So the example we're talking about is pushing a block at an angle across a rough surface. Now you'll remember this was this example problem was the justification for the dot product. And so obviously we're going to have to use the dot product here, but it'll be a little bit more complicated. So you have your surface, assume it's rough. And by the way, when a problem says a rough surface, that implies that there's friction. So we have our block, and let's say we're pushing down on it at some angle theta with the force F. It's just the force that we push on. And the block is moving along at a speed v. We're going to assume the block is constant. Sorry, assume F is constant. We're not going to assume anything about v. V will probably be changing because, you know, if you're pushing it, it might start accelerating or it might slow down if there's a lot of friction, but that's the direction it's moving in. And you're going to keep pushing on it until it gets to the other side. So eventually it'll get over here. And let's just assume that it's still moving, but we're just interested in what happens between these 2 points in time. So this distance here, this distance is delta x, right? This is an example of work energy theorem. Yeah, that's exactly it. Yeah, we finished last time talking about the work energy theorem. So the point is we know that in order to compute work done, we need to know both things about the force and things about the path traveled. Well, in this case, we know what the force is. There's going to be another force too. And we also know the path traveled. It just goes from left to right, a distance delta x. So first, let's figure out the net force. So to do that, we're going to draw a free body diagram like we usually do. So here's our box. We have a force of gravity downwards, which has magnitude mg. We have a normal force upward, keeping the block from falling through the ground, like we usually do. In this case, I'm actually going to put the FG on the other side. We also have a force downward with some angle theta. That's just the force that we're applying. I'm going to call this F push, just so it has a name, so it's not just some arbitrary force, with magnitude F push. And then we also know that there's going to be a frictional force, a kinetic frictional force to the left. Right, it's a rough surface, so there would be friction, and because it's already moving, we're assuming it starts out moving. It's kinetic friction, not static friction. So we can compute the net force on the object. So that would be F push, and now we have to do some trig here. So what's the x component? Oh, let's use these coordinates. We don't have to, but just for ease of use, let's use these coordinates, standard coordinates. So what's the x component of F push? Well, it would be the cosine of theta, F push times the cosine of theta. And then in the negative x direction, we have the frictional force, F sub k. And then we have in the y direction, n, now minus mg. And then there's also the vertical component of the pushing force, so that would be F push times sine of theta. Sorry, this is in the I hat direction and this is in the j hat direction. Right, so that's our net force. That it just is what it is. We could perhaps do some simplification by noting that it doesn't accelerate vertically. So we could perhaps rewrite n in terms of mg and F push and all of that business. But I'm not going to go that far because it won't illustrate anything new. The next thing that we need to know in order to compute the work done is we need to know what the path is. And the path is described by the vector dl. Remember, dl is basically, no, g isn't equal to fg, it's just, yeah, fg is just mg, has magnitude mg. So remember, dl is basically an infinitesimally long path that points in the direction of the path. So you can think of a path being built up by an infinite number of paths that are very, very small. Now, this is clearly not an infinite number, but you would have vectors that point along the path that are very short And so you can imagine just stacking them end on end gives you, or defines the path. So when I say, what is the path DL? DL specifies information about the path through space in whatever coordinate system we choose. In this case, it moves to the right. It moves to the right. And so in our coordinate system that we've chosen, DL, it's just a small length of path. It's just, so imagine L represents a path through space, like a path that something is traveling through. DL is just a very small slice of that, and it points from the previous slice to the next slice. So it's a differential, just like dx is a differential in an integral. So treat it as like a single thing. It's just DL. Yeah, so DL is a vector, has a vector symbol on it. So that means that, and I'm going to go over this in more detail later, but it has a direction. The direction points in the direction of the path, and the magnitude of DL is an infinitesimally long step. So DL tells you what direction should you go in, and the length of the step that you should take, and the length is always infinitesimal. So in this case, we know it moves to the right. So the direction that the step should go in should be to the right. So that implies that DL points in the I hat direction. Now the length of it, well, it doesn't really matter what we call it. It's some infinitesimal thing. Let's just call it dx. So this would be dx in the I hat direction. So the whole point of doing this is that we want to be able to write our path. We want to, the word is parameterize our path in terms of the variables that might be present in the problem. So in our case, we're parameterizing it in terms of the coordinates, x and y. If the block was moving up a little bit, this might be DL might be dx I hat plus dy j hat, for example, if it was moving up and to the right at a 45-degree angle. So actually, you know what? Let me do this in a different way. So instead of using DL, instead of using dx, because that can get things confusing, let's just use DL in the I hat direction. So now this is just the magnitude. Now the magnitude, so we're not integrating over a coordinate here. What we're really trying to do is we're trying to figure out the I'm going to go back on my word. So this whole business of path integrals actually gets tricky. How many of you guys have taken multivariable calculus? Give me an F in chat if you have not taken multivariable. Okay, so a lot of you. So you'll see this when you take 21C, I think. But the whole point is that you're trying to add up things along a path. So normally, when you do an integral, you add up a whole bunch of things. You have a curve, right? So normally you have a curve, and when you do an integral, what you're doing is you're adding up the height of the function above a path across the x-axis. So so you're multiplying the height, the height of that curve. You're multiplying the height of that curve times the width of that rectangle, multiplying them together and then adding them together. So now just imagine we have like three-dimensional path along the ground, right? Imagine here's point A and here's point B. And so imagine that what we're trying to do is we're trying to integrate something else. Say we're trying to integrate f.dl, where dl points along this path. Well, we're trying to add up the force dotted into the dl, which maybe is something like this, along a path. So the f dot part, yeah, I'm talking about line integrals. That's what work is, a line integral. When the f dot part is the function that we're integrating, and then the line that we're integrating over, instead of just being dx, is just some path in space, in three-dimensional space. That's why it's a little bit more confusing. So sometimes you will parameterize, i.e. you will just label how you move, like how you add up along the path. You'll call it dx. especially if you're moving in along the x-axis like we are in this case. But in more complicated cases, sometimes you won't have a single coordinate direction to go in. So you'll just call your individual little steps dl. And then you'll say dl, well, how long, let's say you're traveling up and to the right at a 30-degree angle. Here's x, here's y. How long is dl in this case? Well, you'd have to go and you'd check. So dl would be 30 degrees relative to the horizontal. And so the length would be the third one, that 3D one. No, I mean, path integrals are generally like, that's how you compute work. So you would need to figure out how much of dl is in the dx direction and how much of dl is in the dy direction. And you could do that using trig. So there will be more examples like this, but I just wanted to introduce why, I wanted to explain why I was going back and forth between using dl and dx. In this simple case, you can just use dx because you're just moving to the right in the x direction. But generally, when you're doing these in complicated cases, it gets a little bit trickier. And again, you'll get more experience with this, I promise. Right, so dl in this case, the path that we're traveling along, the little itty bitty steps, we can just call it length dx. It doesn't matter what we call it. We could have called it dw, dq, whatever. It's just the length of little itty bitty steps. The important part is what direction it's in. And that is set by our coordinates. It's moving to the right. And so our coordinate direction says that should be the I hat direction. All right, that was a whole lot for something that's relatively simple. So now we can just go and compute the work. So the work from A to B is equal to the integral from A to B of f net dot dl. This is just the definition of work, right? This is how we defined it on Friday. Now we can expand this. We know what f net is. F net is this whole thing. So, and we know what dl is. So we can just substitute in what we know those to be. So this would be an integral from A to B of f cosine theta minus f sub k in the I hat direction plus n minus f sine theta minus mg j hat dot dx I hat, right? All I did was substitute in what f net is, substitute in what dl is. So dx is now just, it's like a number. It's an infinitesimal number, but it's a number, so it's a coefficient. And so now we just do the dot product. So we know that I dot j is 0. We know that I dot I, come on, erase. We know that I dot I is 1. So we can simplify this. So this is equal to an integral from A to B of f cosine theta minus fk dx. And so because we assumed the force is constant, f, we can just, and we know the frictional force is also constant. That's just a true statement. Well, that's true because the normal force is constant in this case because the gravitational force is constant. So this is equal to f cosine theta minus fk times the integral from A to B of dx. Now, I want to make an important point. Why I wrote hat twice? Well, so dx, so dl is dx I hat, and f net has an I hat in it there. So like there's two vectors in this formula, and then we take the dot product of them. So an important thing to note here, this does not mean integrate from xa to xb. Well, okay, rather, it does mean that, but it doesn't necessarily mean the coordinate x. It means integrate the path from A to B. This is just add up the length along x, add up all of the infinitesimal dx's from point A to point B. So this is just the distance traveled from between A and B. So that's just a delta x there. So that's why we needed this delta x up here. So this is the work done. This is the work done from A to B. And so the reason why we needed that dot product was because note that this is not just, by the way, that f should be f push everywhere. Sorry. I'll just call it f sub p. That it is not just the magnitude of f times delta x, right? if I had found the magnitude of this, I could have found the magnitude of this and then just multiplied it by delta x, but that's not what this is. This particularly isolated the x component of the force vector and the x component of the net force. And the reason it did that was because the motion was in the x direction. So if you want to find the work done, the only part of the work that contributes is the projection of the work onto the direction of motion. And that's why we talked about projections and dot products early on. So I just want to make a quick remark here. So the work energy theorem can really greatly simplify some problems. And the way it does that is, remember that the work energy theorem is a statement. It's the kinetic frictional force. So j dot I hat is 0. So that term just vanishes, because when you do the dot product, you get 0. Unfortunately, Rebecca, I don't think I can. I went over an example, but it'll be in the lecture notes and you can watch the lecture over again. I just don't have time. Sorry about that. So the point that I was making is that the work energy theorem tells us how the change in kinetic energy, 1/2 mvb squared minus 1/2 mva squared, is equal to the work done. So if you can compute the work, for example, if you can compute the work and you know the initial speed, you can compute the final speed just by rearranging that equation, that change in kinetic energy is equal to work done. So the work energy theorem can can greatly simplify some problems, but it can't solve all of them. You can't just replace all of Newton's laws with the work energy theorem and be done. And the reason for that is that there's some information loss. And what I mean by that, let me write this down. There's some information loss. And the wait a minute. Oh yeah, no, that's fine. So it cares about the path taken, right? Information loss. And what I mean by that is we don't learn anything about the direction of motion. We learn nothing about the direction or duration. So why is this the case? Well, think about it for a second. So kinetic energy, which is involved in the work energy theorem, 1/2 mv squared, that doesn't say anything about the direction of motion. It doesn't say anything about the direction that v has, because when you square the velocity vector, i.e. take its dot product with itself, you lose all of the information about its direction. It's just a number now. Similarly, we don't learn anything about how long this motion took, because all we know is information about the beginning and end. We don't know what happened in the middle. So we do lose some information. So if the question is, how long did it take for this block to go from A to B? The work energy theorem doesn't really help us there. We would actually have to solve Newton's equations. We'd have to figure out what the force is, figure out the acceleration, use the kinematic equations, and so on in order to answer that question. But we can still learn things from the work energy theorem, and I'm going to show you how it does simplify problems that we wouldn't be able to do easily with Newton's laws. So let's talk about the work contribution of individual forces. So up until now, all we've been doing is well, at least in this example, we just computed the network by doing a free body diagram, and then we just dotted it and we figured out what we got. So, however, if you recognize that F net, the net force on an object, is just the sum of all of the individual forces, right? That's how we find that. That's what F net means. Then so we can use that fact to rewrite the total work. So the total work, and I'm going to write the subscript W total from A to B is equal to an integral from A to B. This is just how work is defined, F net dot dl. And now we're going to use this information that F net can be broken up into its constituent parts. And by the way, when I say constituent parts, what I mean is things like one of them would be N, one of them would be FK, one of them would be FG, one of them would be F push, right? That's what I mean by its constituent parts. So this is equal to the integral from A to B of F1 plus F2 plus F3 plus so on and so forth dot dl. And we know that the dot product distributes across addition, and we know that the integral distributes across addition. So this is the integral from A to B. Oh, somebody's mic is on. This is equal to the integral from A to B of F1 dot dl plus the integral from A to B of F2 dot dl plus so on and so forth. And so what we can do is we can call each of these the work that is contributed from that particular force. So the total work, and this, maybe it just seems obvious, but the total work is the work from force 1 plus the work from force 2 plus the work from force 3, and so on and so forth. So this is all just to say we can decompose the total work, which is just the net force dotted into the path and then integrated, into the work done by individual forces, and then the total work is just the sum. And the reason why this is helpful is, for example, if the ith force, so maybe it's the 5th or maybe it's the 19th, if the ith force is always perpendicular to the path, to the motion, the path, so consider like you have a force that's pointing one way and then the object is always moving perpendicular to it, regardless of how the object moves. If it's always perpendicular to the motion, then that would mean that F, or the ith force dotted into the path vector dl is 0, always. Total work is the same as, we don't really use the term net work. I would typically say total work, but I mean, they could be the same. So if F sub I, if the ith force dotted into the path is 0, well then the integral of that thing is 0. So that means that the work done by the ith force is also 0. So what it means is we can greatly reduce the number of forces that we have to compute, or that we have to consider. In some cases, anyway. So I'm going to draw a situation that would be hugely difficult to do with Newton's laws. So the example here is a block sliding in a frictionless loop-de-loop. Loop-de-loop. So here's the picture. So you have like a bowl, and then you have a loop-de-loop somewhere in the middle. Right, so block starts off up here, sliding down, and then, or maybe it starts off, I don't know, here, sliding down. It's frictionless, so there's no friction as it's sliding. It comes around, goes around the loop-de-loop, and then it goes back up. Right, and then eventually it'll come to a stop. Right, so let's just say that this distance, let's just call it delta y. So the point is, in this particular example, all of the forces along this path, so if we wanted to do this by computing the total force and then dotting it into the path vector, it would be pretty confusing, because the normal force is changed. Like, remember, the normal force is always perpendicular to the surface. So if they're at an angle, the normal force points out. And if they're at this angle, the normal force points this way. So as the block slides along this path, the normal force is constantly changing. And it also depends on the magnitude of the force of the, both its magnitude and direction are constantly changing, because the magnitude of the gravitational force perpendicular to the surface is also constantly changing because the angle is changing. So you would need to come up with a formula that tells you what the magnitude of the normal force and all of these other forces are as a function of position along this loop-de-loop, which would be really complicated if you wanted to figure out, say, how high it goes after it goes through this loop-de-loop with Newton's laws. And even if you wanted to just find the net force to then take the dot product, you'd have to still know all of those forces. Sorry, if you wanted to do the total work using the net force, you'd still have to know all these forces. However, one important thing to note is that the normal force is always perpendicular to the surface. And the direction of motion is in the same direction as the surface. This implies that the normal force is always perpendicular to dl, the path vector. So what that means is that the total work. So in this case, there's only two forces. There's just the normal force and the gravitational force, since there's no friction. The total work, which is just the integral from a to b, which would be the normal vector minus mg, say, in the j hat direction. Let's just give some coordinates, x and y, dotted into dl, and we still don't know what dl is. DL would be complicated too, because dl is constantly changing directions and so on. We know that this bit, that dot product, is 0, because the normal force is perpendicular to that vector. So this is just equal to minus mg, integral from a to b, of j dot dl, j hat dot dl, sorry. Right, m and g are both constant. They're just mg like normal. J is the j vector, and dl is the thing that's constantly changing. It tells you the direction of the path that the object is taking. Now, this is great because we didn't have to know what the normal force was. That's definitely a win. But this is still fishy, right? Because we don't know what dl is. But if we think about this for just a moment, and we're going to talk about this in more detail. What is the integral of j dot dl? Well, so dl tells us both the magnitude and direction that we go in for each infinitesimal chunk of path. Now, if we dot that with the j hat vector, that would give us the projection of the dl vector in the y direction. And the reason it's just the projection is because j hat has unit length, so we don't have to multiply by the length of that vector. So this quantity, j dot dl, this is the projection of dl in the y direction, like along the vertical axis. So if you add up the projection that, so imagine that you have a whole bunch of different dl's that are adding up end on end, right? Imagine this is part of the loop-de-loop. The projection would be this bit. It'd be that bit, and then that bit, and then that bit, then that bit, and then that bit. But the point is all this does is it's just adding up the length that the object has gone upwards. So j dot dl tells us just how far up did the path go during that infinitesimal interval, and then you add them all up, and so you get the total distance, the total vertical distance, sorry, the total vertical displacement that the object underwent. So in this case, so that would indicate that this is just delta y. It is just the vertical displacement between B and A. Because all we're doing is we're just adding up we're only adding up the vertical contributions. We're integrating the vertical contributions to the path. And sometimes the vertical contributions will be negative when it goes down. Sometimes the vertical contributions will be positive and then negative again in the loop. Then it'll go back up. But the end result is we're just adding a little bit of dy, then subtracting a little bit of dy, then adding a little bit of dy. But at the end of the day, we're just adding the amount that's gone down and plus the amount that's gone up. And that is just delta y. It's just the final height minus the initial height. So what that tells us then is that the total work in this particular scenario, that's not a vector, sorry, is just negative mg delta y. Now, in the lecture notes, I'm going to go into a little bit more detail. So if you want to see this in more detail, this argument of how this integral of j dot dl is delta y, check the lecture notes. I kind of explained it in words. Not necessarily, they won't necessarily be given, but that is what it's equal to. I kind of explained it in words, so, but if you want to see it like written out more, go check the lecture notes after lecture. The important point though, and this is remarkable, yes. I mean, that's just how we defined it, right? It's the distance between the initial and final height. No, that's not the point I'm getting at. Actually, Maximus, we're going to get to more detail onto when this is an appropriate thing to do in a minute. So a remarkable fact is that the work done by gravity doesn't care about the path taken. It only cares about the initial and final positions. So let me just explain that just a little bit more. So when we did this computation for the total work, the normal force, the amount of work that, or the work that was contributed by the normal force was 0. So this total work that we computed, that's just the work done by gravity, because the normal force just doesn't contribute anything. And so what we found is that this work, the work contributed by gravity, the work done by gravity, only cared about where the object started, A, and where it ended, B, because that gives us enough information to find delta y. So, and it doesn't matter that there was a loop-de-loop in the middle, because any amount that it went up during the loop-de-loop, it also went down that much, right? So it could have been any confusing path that it took. Gravity will always only care about where you started and where you ended. And the reason for that is that once you isolate the work done by gravity, like we did here, what you'll end up with is whatever you're calling your vertical unit vector, j, in this case, dotted into the path. And that will always just be the vertical displacement of that path by this type of argument that I just made. And so this is an amazingly useful property of gravity, and other forces also have this property, but not all of them. So let me write another sentence. This property that it only cares about the initial and final positions, the work done by that force only cares about the initial and final positions. This property is not true for all forces, or this property does not hold for all forces. But those which have this property are called conservative. They're called conservative forces. Not in the political sense, just in the conservation law sense. So gravity would be an example of a conservative force, or the force of gravity anyway. So there's a weird consequence of these sort of conservative forces that I should probably tell you about. If an object takes a path such that it starts and ends at the same place, regardless of the path taken, a conservative force does no work. So think about gravity. Even if there were a whole bunch of crazy loop-de-loops, if the object started at height A and ended at height A, because the difference in the heights would be 0, I'll give you an example of a non-conservative force today. Because the difference in the heights would be 0, it doesn't matter what happened on the interim. It'll just, the net force will be 0, or the total work will be 0. And so in particular, if you start and end at the same location, if you say go down a hill and then come back up the hill and so on, your position is the same. So your height will have been the same initially and finally. So the work done will be the same. And this is true for all conservative forces, because as long as they only depend on the initial and final positions, and in particular, it will depend on the change of some property of your initial and final positions. So like if some force cared about your horizontal position, as long as your initial and final positions are the same, that change in whatever position property you're talking about, the change in that thing is 0. So mathematically, we might write W conservative, I'm going to abbreviate it cons, of A to back to A. So this isn't just sitting still. It could be traveling in a crazy loop and then going back to A, right? This is equal to the integral at A, f dot, or actually I'm not going to write the subscript there, f dot dl, and this is f cons. This is equal to 0. So you guys may not have seen this notation before. That circle in the integral sign, the circle means around a closed path. And what a closed path is just a path that closes back in on itself. So it starts somewhere, it goes, and then it comes back to itself. So like it's like it'd be like a loop of string rather than like just a loop of string that's like tied back to it, where the end is tied to the beginning, rather than just like a string that's just like laid out, not connected back to itself. Any conservative force going around a closed path does no work. So we can show this explicitly. I can prove this to you by doing an example. So a ball is thrown, let's just talk about gravity again. A ball is thrown upwards. Upward, and then it's caught at the same height. Practically speaking, you won't actually have to do a lot of these complicated integrals, but you need to know the foundation, so then you can do the simpler ones. So how much work does the gravity do? Or how much work does gravity do? So we're going to assume that like it leaves your hand at like the position A is right as it's leaving your hand, so it has that initial velocity. And then position B is right before it hits your hand, so like your hand doesn't do any forces. What work does gravity do? So the work done by gravity, so W sub G, from the hand to the hand, well, we could just go and compute this, or we could just say, oh, it's 0 because gravity is conservative. But I want to show you that it's in fact 0. So this is the work done. Remember, so let me back up. So just like when you're doing integrals, an integral from A to B plus an integral from B to C, that's an integral from A to C, right? Like you can always split up the bounds of the integral, and you can do that with path integrals too. It works just as well. So what we're going to do is we're going to split up the work integral into an integral from hand to the air, to the top, like when it's at the top of its. And let me draw a picture actually. So here's my hand. Ball is thrown up. Here's the position when it's at position air, and then ball comes back down. So for the first part of the journey, dl is up. For the second part of the journey, dl is down, right? And let's just use plus y for the vertical. Right, so this would be plus the work done by gravity from air to the hand. Now, in general, they do not have to be equal and opposite, like they don't have to cancel. Turns out that they will though. So this is an integral from position hand to position air minus mg j hat, because that's the force of gravity on the object, dotted into the path that it is going, which is dy j hat. So it's going upwards. So the length of its path is dy, and it's traveling in the plus j hat direction. Then we add to this the integral from air to hand, and it's minus mg j hat because the force is still the same. And now as the ball falls from the air to the hand, the path it's taking is in the negative j hat direction. So this would be minus dy j hat. All right, so let's do this integral. So j hat dot j hat is 1 in both cases. So we have minus mg integral from hand to air of dy plus, and we have two minuses, so this is going to turn into, so this is going to stay a plus, plus mg from air to hand. And this is where it's going to get confusing, I promise, but it'll all make sense. Dy. So you might say, oh, well, this is at some value and this at another value. So these things shouldn't cancel, right? Because even though they have opposite signs here, the integral, the bounds of integration have flipped. But the important point to make is that this is not an integral over some coordinate position. This is an integral, like, and this is why I brought up that whole business with calling it dl. Actually, if I simplify things, I'll actually just call it dl here instead of dy, just to avoid confusion. So dl is just the length that it travels upwards, but it's traveling upwards. So the fact that it's going in the y direction is captured by the j hat. So let's call this dl and this dl. This will make it a little bit easier to explain. So this is just an integral of the length that of the length from the hand to the air. So this is just equal to the it's just minus mg, and I'm going to call this distance here delta y again, delta y. So that is like, this integral is just the path length from the hand to the air. And then this integral is the path length from the air to the hand. Now, importantly, those are both positive numbers. They're both just path lengths. That's why I wanted to avoid using y here rather than, or instead of L, because if you use y, it'll make it seem like that these are coordinates. We're not talking, these do not represent coordinates, they just represent positions. So this is also delta y. And so then this whole thing cancels out and gives you 0. And we can talk more about this after lecture and in the office hours, but it's an important point to make. Oh, we got to keep going. All right, so another example of, so by the way, that's just a simple example showing that the work done from point A to point A is 0, because the work going up and the work coming down added together, or they cancel each other out. And that's because it just depends on the change in position. So let me give another example of a conservative force. In this case, the elastic force is conservative. Not in this case, that's just generally true. So I want you guys to remember Hooke's law. Hooke's law was a statement about the force from a spring or from something that's elastic. And the vector equation was negative k delta x, where x is a vector that points, and actually I'll just write it out, where delta x is the vector that is displacement from the equilibrium position. So you just find the displacement vector from the equilibrium position to the new, or to the current position. So let's compute the work done by a spring on a block as the spring is compressed. So example, compressing a spring. Let me draw a quick picture. So we have our block with our spring attached, or our wall rather, sliding along the ground, say. And let's say that, like, maybe it's not starting at equilibrium position. Let's just call this x equals 0. That is the equilibrium position. By the way, for these types of problems, it's often useful to just call the equilibrium position your origin, because that's nifty. And we'll call this place x equals xa. It's going to be our initial position, so it kind of makes sense. And then the block is going to slide to the right. So it's already starting to be compressed. We're going to compress it more. So that's position A, and then position B will be after it's compressed. And we want to figure out the work done by the spring, not by the person pushing it, the work done by the spring, between positions A and B. So let me redraw the block. It's more compressed now. So this is x equals xb. And maybe it's still moving, maybe not. It doesn't really matter. Okay, so the work done by the spring. Oh, so let's figure out the force. So if the block was at some arbitrary position, say x, then, and let's say that x is positive, for example. Let's say the block is like here, and that's just some random position x. Right, so the force should point to the left, and it should have magnitude k times the distance between equilibrium and the position it's at. So in fact, the force by the spring should be negative k times its position x times I hat. So one way to one way to check this is to just think about it. So say it's at position xa. Well, xa is a positive number. So the force, when it's at position xa, would be negative k times xa, which just is what it is. It would point to the left because xa is positive. And so we do know that the spring force does push it back towards equilibrium. It's being compressed. As it gets further to the right, we can check again that this spring force makes sense. xb is larger than xa, and we know that the spring force should get larger as it gets more and more compressed. So because xb is larger than xa, when you plug that in for x, you'll get a larger force to the left. So this is a good way of writing the force for a spring. It's not always this. It's just negative k times the displacement vector. In this case, though, our origin is at x equals 0, and the displacement vector is always in the x-axis. So the displacement is just x in the I hat direction. All right, now let's compute the work done by the spring from A to B. So this is an integral from A to B of F spring dot dl. Now we really want to write this in terms of a variable. We want to parameterize the path that it takes in terms of x, because as the path moves at different places along the path, the force changes. So we would write that this is from an integral from A to B of minus kx in the I hat direction, dotted into dl in the I hat direction. It's moving from left to right. But what is dl here? Well, along the path, we can choose a coordinate so that dl is just equal to dx. That's a totally fair thing to do, as long as we change b into the position b. So basically, L is associated with A and B. X is associated with XA and XB. X is the position along the horizontal axis of the block. So this integral would be minus k of from XA to XB of x times dx. Yeah, k is just a constant. And so we can do this integral. This is minus 1/2, and I'm going to do some fancy factorization here, nothing super fancy. 1/2 kxb squared minus 1/2 kxa squared. And so you could write this as minus 1/2 k times the delta of x squared. Yeah, so it's not a hard integral. But the important point is that this is just the change in the square of the position. So this isn't identical to the gravity case. In the gravity case, it was minus mg delta y. Here, it's minus 1/2 k delta x squared. But the important point is that this still only cares about the initial and final position. Which is just a demonstration that the elastic force is indeed conservative. And so it'd be easy to see that the round trip criterion, i.e. if you do an integral from A back to itself, the force would be 0, because it'd be xa squared minus xa squared. We're almost done. I have like half a page left of notes, and then we'll be done. So I'm just going to go for a minute more, because I wanted to give an example of a non-conservative force. An example of a non-conservative force is kinetic friction. Did not mean to cross out what I wrote. So let's just look at the simple case of a block sliding back and forth on a rough surface. So it starts off at position A, goes to position B, and then it goes back. And you have a block sliding back and forth. I'm not going to draw the box. And let's just call this the plus x direction, just to make things easier. So when it's moving right, F sub k, this is the frictional force. The frictional force points in the opposite direction of the direction of motion. So this would be negative mu sub k times n in the I hat direction. It points to the left, and n is just the normal force, whatever it is. When it's moving to the left, F sub k would be mu sub k. It would point to the right. So it'd be mu sub k n in the I hat direction. So the total work done from A to A, sorry, I'm going quick. I just want to finish up so you guys can leave. From A to A, if it was conservative, it would be 0. We're proving that it's not. This is the work from A to B plus the work from B to A, right? So the work from A to B is an integral from A to B of minus mu k n I hat dotted into, let's say dl I hat direction. So the small length of path dl, or small length of distance traveled dl in the I hat direction. And then we have plus an integral from B to A, mu k n I hat, that's the force, dotted into, now the path here is, it still has length dl, but it's traveling in the negative x direction. So now we can just simplify. Mu sub k times n is constant. I hat dots into itself to give 1. So this is negative mu sub k n, integral from A to B of dl, plus, or minus mu sub k n, integral from B to A of dl. Now, again, these do not cancel because these are not flipped. This dl represents the distance traveled between the bottom and the top, and a distance traveled is always positive. So this is minus mu sub k n times, let's call this distance delta x, times delta x, minus mu sub k n times delta x, which is just negative 2 mu sub k n delta x. And importantly, it's not 0. So really, the friction always does negative work. It will always reduce the kinetic energy that you have. And so this would be an example of a non-conservative force. A good check if a force is conservative or not, if you can find an example that makes it so the closed loop criterion isn't met, so that if you go from A to if you take a path that starts and ends at the same place and you don't get 0, then you know it's not conservative. And so in cases like this, the path matters. The path taken matters. And the reason how you know the path taken matters is just by imagining a case where an object takes a really long path on a frictional surface. The longer the path, the more negative work there is. So it depends not just on where you start and end, but it also depends on how long you took to go from A to B. All right. So I didn't get a chance to talk about power. I'll talk about that on Wednesday. I don't think there's any problems about power on the homework, but I will. I'll double check the homework and make sure there aren't. And if there are, I'll make sure you don't have to do that. All right. So I'm going to stop the recording. Sorry.